So in section 2.4, we are identifying the real zeros of a given polynomial function. And you guys already know how to do this for quadratics by either factoring or quadratic formula. But now we're going to be looking at finding the real zeros for higher degree polynomial functions. So we're going to be factoring a polynomial function over the real number system. And that will allow us to then identify the real zeros of the polynomial function, which then we can take those real zeros. We know those correspond to x-intercepts of on the graph of the polynomial function. We'll be able to sketch the graphs. So we're going to start with the remainder theorem. So what the remainder theorem says is if a polynomial p of x is divided by x minus a, then the remainder is whatever the polynomial is evaluated at a. So the theorem tells you that the polynomial division can be used to evaluate a polynomial function at a particular point. So for example, if we were to divide x cubed minus 2x plus 4 by x minus 2. And we could use synthetic division to find that quotient. And we can use synthetic because we're dividing by x minus 2, which is in the form x minus a. So using my placeholder, I bring the 1 down. 1 times 2 is 2, add straight down. 2 times 2 is 4. Okay, so we end up with our remainder being 8. Okay, so now if we were to think about the polynomial that's the dividend, so x cubed minus 2x plus 4. And if we were to evaluate that polynomial at 2, we end up with 8. Notice that 8 is also our remainder whenever we do division, polynomial division. So here's what the remainder theorem says, right? This is an example of what the remainder theorem says, that if a polynomial is divided by x minus a, right, a divisor that's in the form x minus a, then we know that the remainder will be the polynomial evaluated at a, which is what happened in this example. So the remainder theorem leads us to the factor theorem, right? So if we think about the remainder, like what if the remainder is equal to 0? Well, that would mean that p evaluated at a would be equal to 0, which would make a 0 of the polynomial, and therefore x minus a factor of the polynomial. Okay, so factor theorem is based on the remainder theorem. And then this is a typo. This should say, conversely, if x minus a is a factor of p of x, then p of a is equal to 0. Okay, so if we want to determine whether x minus a is a factor of this polynomial, by the factor theorem, we could evaluate p of x at 1. And we're looking to see if p of 1 is equal to 0, which would make 1 a 0. So 1 minus 4 is negative 3, minus 7 is negative 10, plus 10 would be 0. So what do you know? Therefore, by the factor theorem, x minus 1 is a factor of p of x. Okay. you could also divide x minus 1 into the polynomial p of x to see whether or not the remainder that you get is 0, which we would expect it to be, right? And so since we have x minus a as the divisor, we can use synthetic. Could use long division too, but we might as well use synthetic when we're able to. So 1 times 1 is 1. Add straight down. Add straight down. And just like we expected, we can see that our remainder is 0. Now remember that these numbers correspond to coefficients of the quotient. So we can tell, because this remainder is 0, that x minus 1 is a factor, but we can also now think about rewriting p of x as x minus 1 times x squared minus 3x minus 10. And then since x squared minus 3x minus 10 is a quadratic, you guys know how to factor that. So now we've just factored the polynomial completely, which is helpful because now we can identify, we can see that the real zeros would be 1, 5, and -2. Each have a multiplicity of 1. Those correspond to x-intercepts. So we can just do a lot more whenever we test whether or not a factor is a factor, whether or not a polynomial is a factor of another polynomial using either long division or synthetic division. Because if it is a factor, then we can find what times that factor would give us our polynomial. Okay, so we want to determine whether x minus 3 and x plus 2 are factors of p of x. And if they are, we want to factor p of x completely. So you can either use the factor theorem or remainder theorem to see if when you evaluate p at 3 and at -2 you get 0, but that doesn't really help you towards factoring the polynomial. So why don't we just go straight to using synthetic division. So let's test first to see if 3 is a factor of p. Or sorry, if x minus 3 is a factor of p. So I'm going to put 3 up in the left corner. Okay, bring 1 down. 1 times 3 is 3. Add straight down. Oops, that is not what I meant to do. That should be -6. 6 plus -6 is 0. So after doing this synthetic division, we can now rewrite p of x as x minus 3 times, what is that, x cubed plus 2x squared minus x minus 2. And then we now want to see whether or not x plus 2 is a factor of p of x. Well, if x plus 2 is a factor of p of x, then it should divide evenly into x cubed plus 2x squared minus x minus 2. So instead of doing synthetic division with the coefficients of p of x, I'm going to do synthetic division with these coefficients of x cubed plus 2x squared minus x minus 2. Okay, bring the 1 down. And we can see that we get a remainder of 0, which means that p of x can be written as x minus 3 times x plus 2 times x squared minus 1. Well, you guys know what x squared minus 1 factors to. I'm going to move this over here so I can keep going. So since x squared minus 1 is the difference of two squares, that'll factor to x minus 1 times x plus 1. So now we have factored p of x completely over the real numbers. And we can now easily identify what the real zeros of p of x are, right? They're 3, -2, 1, and -1. So a polynomial function cannot have more real zeros than its degree. So think back to when you guys studied quadratics, right? Quadratics are second degree polynomials, and their graphs we refer to as parabolas. Well, parabolas can have two x-intercepts, meaning they can have two real zeros. They can also have one x-intercept, meaning one real zero. Or they could have no x-intercepts, which would mean no real zeros. But they can have at most two real zeros, and they are second degree polynomials. So like a third degree polynomial can have at most 3 real zeros. A fourth degree polynomial can have at most 4 real zeros, and so on. We are going to be using the rational zero theorem, also known as the rational root theorem, to help us with factoring polynomials. So we're going to take all of the positive factors of the constant term of the polynomial and list them over all of the positive factors of the leading coefficient, and then list all the different combinations from there, plus or minus, okay? So let's get into an example. So if we want to list all of the possible rational zeros, this does not include irrational zeros, this is only rational zeros. In this case, it would be plus or minus. We look at all the factors of the constant, -3. The positive factors would be 1 and 3. The leading coefficient here is just 1. So the only possible positive factor of 1 would be 1. Okay, so the only combinations we have are plus or minus 1 or plus or minus 3. I'm okay with you guys just putting the plus or minus in front and then listing the positive version of the possible rational zeros, just so you don't have to write plus or minus over and over again, because sometimes there's a lot. But it should be understood that your possible rational zeros are +1, -1, +3, -3. So then you can take those possible rational zeros and you can test whether or not they're zeros with synthetic division. You could also evaluate the polynomial at those numbers to see if you get 0. But if our goal is to factor a polynomial completely, which is what it usually is, then we want to test using synthetic division. So like if we start with +1, bring 1 down. Oh, okay, so 1, it's a sad faced. 1 is not a 0. So maybe let's try -1. I feel like something's going wrong. Did I do something wrong over here? 1, 2, -2, 2, -3. Let's try 1 again. So I thought that should have worked. Yep. Oops. Okay. So 1 was actually a 0. I just made an arithmetic error. Okay, so we know that right now that we can rewrite p of x as x minus 1 times x cubed plus 3x squared plus x plus 3. And then we can move on and test another possible 0. And you don't need to go in the same order, or like you don't need to necessarily go in order. Like I can choose to test -3. And I'll explain in a second why I want to test -3. Let's bring the 1 down. Okay, so p of x can be written as x minus 1 times x plus 3 times x squared plus 1. And now the reason that I wanted to test -3 is because I saw that x cubed plus 3x squared plus x plus 3 could actually be factored using, or factored by grouping. Remember factoring by grouping? So if I were to group x cubed plus 3x squared and then group x plus 3, I could do that by the associative property of addition. And then if I factor out the GCF of the first grouping, this, remember, is 1 times x plus 3. Now I have common binomial factor that I can factor out. Okay, so I could see that -3 was going to be a 0. If you see that you can factor by guess and check or grouping, go ahead, do it. You don't need to keep using rational root theorem. But if you don't recognize that, then that's fine. Just keep using rational root theorem and synthetic division. So we've actually factored as far as we can go now because x squared plus 1 is what we call an irreducible quadratic. So x squared plus 1 cannot be factored over the real numbers. X squared plus 1 can be factored over the complex numbers. It can be factored to x minus I times x plus I. And in section 2.5, when we're looking at identifying all of the complex zeros of a polynomial, we will be factoring further. But right now we're just in the real numbers, so we are going to stop at x minus 1 times x plus 3 times x squared plus 1. Okay, so we can see that the only real zeros here are going to be 1 and -3. Okay, so we want to factor this polynomial completely. Sorry, my cat just came in here. Hold on. Garbo. Come on. Get out there. Get out there. Okay. Okay. So we want to factor this polynomial completely. So let's use rational root theorem. So listing all the possible rational zeros. Okay, I'm listing all the possible positive factors of 6. Oops, forgot 2. And then leading coefficient is 1. I'll show you guys an example where we need to list all the possible rational factors when the leading coefficient is not 1. So plus or minus 1, 2, 3, or 6. So a lot of possible rational zeros. It's usually best to just start with positive or -1. So let's just start with 1. Oh yeah, that is -6. Okay, so +1 didn't work. -1. Yeah, looks like +1 doesn't work. So we can try -1. There we go. So -1 works, meaning x plus 1 is a factor of p of x. So p of x can be written as x plus 1 times x cubed minus 3x squared plus 2x minus 6. You can always check to see whether or not you can factor by grouping or guess and check. This guy could be factored by grouping, or we can keep using our rational root theorem. So my suggestion, if we keep using rational root theorem, would be to test +3. And you know what? Since the coefficients, we're seeing if x minus 3 divides into this factor here. I'm going to set this up like this. Just so I don't have to rewrite those factors again. Oops. Okay. So x minus 3 works. So p of x can be written as x plus 1 times x minus 3 times x squared plus 2. And x squared plus 2 is an irreducible quadratic. So we are done. We have written p of x in factored p of x as far as we can over the real numbers. Right, because x squared plus 2 would be an irreducible quadratic. Now I knew to test 3 because I could see that you could factor this guy using grouping. So I saw that x minus 3 was going to be a factor, but if you didn't, you could just keep going. Like you could test +2, -2. It can kind of be a guess. If you want to read about Descartes' rule of signs, that can help you narrow down the values you should be testing a little bit. But I am not requiring that you learn about Descartes' rule of signs. But it is in your textbook. Okay, so we want to be able to sketch the graph of f of x. Okay, so we need to be able to first identify the real zeros of f of x by factoring f. And then we know that those will correspond to the x-intercept. So we list by rational root theorem. Let's list our possible rational zeros. Right, so I'm looking at the factors of 6. Leading coefficient is 1. Might as well test 1 first. Okay. Okay, so x minus 1 will be a factor. And then x minus 1 times a quadratic, so we will be able to use guess and check to factor the rest of f. X minus 2, x minus 3. So we have factored f completely over the real numbers. We can see that our real zeros are 1, 2, and 3. The multiplicity of each zero is 1, right? Because each of these factors is raised to the first power. So our x-intercepts are 1, 0, 2, 0, and 3, 0. And the graph will cross straight through at each of those x-intercepts. Let's think end behavior. So this is a third degree polynomial, so an odd degree polynomial with a positive leading coefficient. So our end behavior will be like a line with a positive slope. Okay, so I graph the intercepts, I know the end behavior, and I know at each x-intercept the graph will cross. We don't have calculus, so we don't know how far up or down the graph will go, but it'll end up looking something like that. Oh, we could identify the y-intercept, right? The y-intercept in this case would be 0, -6. So it'll cross down at 0, -6. Now before we graph this last polynomial, I do want to give you guys an example of a polynomial with a leading coefficient other than 1. So let's say okay, so let's say that's our polynomial, and we wanted to factor using rational root theorem. So then we list the positive factors of 7, -7, so 1 and 7, and then the factors of 2, so 1 and 2. So our possible irrational zeros are plus or minus 1, plus or minus 1/2, plus or minus 7, and plus or minus 7/2. So it's all the different combinations you could get, right? So 1/1, 1/2, then 7/1, 7/2. Okay. So let's go back to this guy. So rational root theorem, factors of -12, positive factors of -12. So 1, forgot 2 again. So 2, 3, 4, 6, and 12. Lots of them. Okay, so plus or minus, our leading coefficient was 1. Let's start with positive 1. It's usually best to start there. Yay. Okay. Now, don't forget that you can have factors or zeros that have multiplicities other than 1, right? Remember, we can have repeated zeros or repeated roots. So sometimes if you go through your entire list of possible irrational zeros and your polynomial is still not completely factored, you want to go back to one of the zeros that did work and test them again to see if maybe there's a repeated zero. Some people also use the strategy of like for example, if 1 worked, they'll test 1 again to see if it's a repeated factor. It's kind of up to you on what strategy you want to use. I want to test -3 next. You may see why that is, or you may not. You can always just, if you want to do -1, you could. It's up to you. I'm not going to rewrite these again, actually. Let's move this up like I did before. Yay. Okay, so p of x can be written as x minus 1 times x plus 3 times x squared plus 4. X squared plus 4 is an irreducible quadratic, so it can't be factored anymore. So the real zeros for this polynomial are 1, -3. Both have a multiplicity of 1. So the x-intercepts will again both cross. The y-intercept of -12. Let's say -12's down here. Okay, it is a positive, so it's a fourth degree polynomial, positive leading coefficient, so end behavior is going to be both ends up, right? As x approaches positive or negative infinity, y will approach positive infinity. Now here's the thing, we don't know what happens down here. It could just go curve down and look almost like a parabola. It could kind of have some extra curves. You will not know without calculus what really happens beneath the x-axis in this case. Okay, once you have calculus, so next year you guys will be able to determine where the graph would change, like where the highs and lows of the graphs are, and where the graph changes from concave up to concave down. So you'll just be able to get a more accurate picture of the graph. So for now, this is the best we could do. And even this is just a guess. I don't know what's happening really. So it's just a guess. So we've used everything in our toolbox to be able to sketch this graph. We could do test points, so it would give us a little better picture, but still. Test points don't necessarily tell you key features of a graph.